差一个函数了，就是说哈密顿不是唯一的。
Yeah, sure.
为什么呢？
So, I mean, to begin with, your Hamiltonian 对应到的是你的 energy, right? You can actually shift your energy level where you are measuring.
我知道你意思，可是如果它差那个常数是跟那个无关的话，我可以接受。可是它那个常数是跟位置有关系的，就是这样的话，你的运动方程就会变的。
Right, so therefore that's not the same trajectory.
对 ，we make it， 我们可以下来讨论。
Yeah. Okay, so as a quick example, so let's look at a system with 1 degree of freedom. So therefore the phase space M is 2-dimensional. Okay, so and we describe the system by a generic Hamiltonian with kinetic energy and potentials. Okay, so almost by definition, the Hamiltonian commutes with itself, or Poisson commutes with itself. So that means the Hamiltonian itself is a constant, or is conserved in the time evolution. So we can set the Hamiltonian, this guy here, given by a constant. So actually, so the phase space looking something like this. Let's give it an axis P, Q. So once you specify the value of E, then basically the equation H equals E, well, sorry, I should say for this case, that would be the case of BQ, which is a familiar simple harmonic oscillator. Then for this case, the trajectory of a constant energy in the phase space is simply given by a ellipse. Okay, but generally we can deal with a more complicated potential. Okay. So anyway, so since energy or the Hamiltonian is conserved, we can express the momentum in terms purely of the position just by direct substitution. And the Hamiltonian equation of motion is given in this case by Q dot equal to P and P dot equal to minus dV over dQ. Okay. So the solution of our problem, now we know that precisely because energy is actually conserved, we can actually substitute away P as purely a function of Q. So therefore we have Q dot equal to 2E minus VQ, or so we can actually perform the integral from certain reference time t0 to the particular time we carry about. Let's just call it t, so we will dummy variables. That. So you evolve that from some reference point q0 to the position at the time t you care about. And that's basically the answer of your system. Okay, so whether you can actually perform this integral, that's a different matter. That really depends on what kind of function VQ you are using. So, for example, for the simple harmonic oscillator, which I brought up just now, which goes at omega q squared, then the solution is basically given by P dot pt you can obtain just simply by taking a derivative. Okay, so I hope you have seen this manipulation, like by putting certain dynamical variable, in this case just simply the energy, which a lot of time you actually assume to be constant a priori anyway, and use that via the substitution to actually solve your Hamiltonian equation of motion this way. So, seen this before? I do expect some response. 这有看过吗？没有看过 ？Don't care. Whatever. Okay, fine. Okay, so I hope at least this example actually illustrates that even without knowing anything about integrability, which I haven't said anything, to be honest, that if you have certain quantities conserved, then that actually gives additional constraint into your otherwise, higher dimensional, basically multivariable evolution equation. But now if you impose a constraint that allow you to actually, reduce the equation of motion to something a lot simpler, then you can actually do it by simply perform a elementary integral. Okay. And that's why a lot of time that in various kind of physical situations, the first thing physicists ask about is what are the conserved quantities that are in your problem, and also a lot of those conserved quantities precisely to do with you have various kind of symmetries in your system. For example, like conformal symmetries that Yongchen was telling us yesterday, and also that in a lot of kind of modern high energy research, that a kind of symmetry that is widely used is supersymmetries that give you additional constraint to actually solve your to allow you to solve your the dynamic of your system in a much straightforward fashion. Okay. How we do this time? Okay. Okay. So now I would like to enter probably the most important topic of this morning's discussion. That is the so-called Liouville theorem. Okay. So now, given a phase space M of a dimension n, so basically you have coordinate qi, ei, I1 to n. Okay, so on this phase space, we can define a closed Q form sometimes goes in elliptic form. Which is simply given by the wedge product of P with D. So closed simply means that D omega goes to 0. So this statement simply tells you that you can actually define a Poisson bracket on your phase space. So if you are not familiar with the differential geometry notation, then don't worry about it. So, or you can just read it as, okay, so Poisson bracket exists. Okay, so, okay, so the definition of a Liouville integrable system So definition of a Liouville integrable system is that the system is said to be Liouville integrable if for this system carry n degree of freedom, that it has an independent and commuting, well, okay, yeah, let me just write it step by step. Has n independent conserved quantities Fi, so basically equal to 0, and such that, so they are not only independent, but also they commute, Poisson commute with each other. So if you calculate the Poisson bracket between those, say, two given conserved quantities, the Poisson bracket vanishes. Okay? So the independence here simply means that F are really, like I said, that they are really dynamical variables in your system, therefore they are functions on the phase space. And the independence here simply means that if you look at the vectors associated with, say, each of the functions, they are orthogonal to each other. Okay? So basically they allow us to define a vector space over at every given point in your phase space. Okay, so that's what independence means. Or basically, if you want, their partial derivatives are not linearly dependent on each other. That's another way if you write out in the coordinates. Okay, so, and the Liouville theorem simply states that so the most important thing you need to remember about a Liouville integrable system is that the following two things are true. And for a lot of time, that H is actually one of the F's, or basically a function of those F's. So therefore, if this is true, this implies this is also true. Okay? So, but anyhow, so the so-called Liouville theorem states that the solution to the equation of motion to the Liouville integrable system of a Liouville integrable system is obtained. So basically, a system satisfied whose conserved charge satisfy all this Poisson commuting condition is actually obtained. Sometimes in literature they say by quadrature. But in terms of plain English, that simply means that, well, by finite steps of algebraic operations, such as doing the integrate, and such as doing subtraction, additions, multiplication, etc., and integration in terms of some known functions. Of course, whether you can perform this integral or not, that's a different matter, but you can write down the expression. Okay, let me try to just tell you what this actually says. All right, so basic idea is that given a Poisson bracket, or basically a differential, a symplectic form on a phase space as such, we can find, so basically, yeah, okay, let me just try to see. So we can find a canonical transformation. Do people know about canonical transformation? Do people do not know about canonical transformation? Those who do not know, raise their hand. Okay, again, it's minority, sorry. So do look it up. Or just, you can connect to internet or something. Okay? So we can find a canonical transformation taking you from Qi, Pi, to another coordinate choice, which is basically Fi, and another thing called psi I. Fi is basically our conserved charges in the system. So to remain canonical, by definition, that this thing can be rewriting. We can rewrite it as Df, d psi. Okay. So what's the point of doing this? Well, so if you can actually find this canonical transformation and mapping your Q and P to here, think about what are the Hamiltonian equations for F and psi, then you realize it's that simple. Because now, if you look at the Hamiltonian equation for, do I guess, I don't know, 0. So if you look at Hamiltonian equation of motion for Fi, or I'll call it Fj here, then by definition, it's a conserved quantity. Therefore, this thing is 0. That basically tells you that Fj at any given t is simply given by its initial value, or basically a constant. Okay? And also, if you look at the time evolution for psi, okay? Again, if you compute the Poisson bracket, which is basically this guy, and the point is that the Hamiltonian can actually be expressed as a, so actually I did assume about the independence, and also there's an implicit assumption that the Hamiltonian can actually be expressed as a function of those conserved quantity f. So the punchline is that if h is a function of f, then this thing is again, because f is constant, this thing is also constant. So the time evolution for the psi is simply given by omega t plus some initial constant. That's the answer, basically. So that's why people are looking for conserved quantity. And that's why they've got to reduce the problem to really just simply writing out set of constant and then you just have a linear flow, right? It's a linear dependence in time in the phase space. And the punchline is that, well, how can we find this, whether such a canonical transformation actually exists or not, okay? And the punchline about Liouville's theorem, it simply says that, well, if the following condition actually satisfied, then that implies the existence of such a canonical transformations. That basically proves and shows the existence of those guys. Okay? So, is it okay if I go 5 minutes over into the break, then I can finish a proof? Okay, so let me try to prove this statement, okay? So, any question about like the statement of the Liouville theorem that's unclear, or we all good? We good? Okay. So let's see. Okay, so the question is about whether the canonical transformation actually exists. So to construct such a canonical transformation, we consider something called a generating function S, which is simply given by an integral. So yeah, let me just state it first. That is given by integral of the following expression. So if you want, you can just read it as a line integral, which P now is actually a function of Q. But otherwise, at the moment, P and Q are actually independent coordinates in the phase space. So we are doing the integral in the phase space from some point, let's say, Q1, actually I should call it Qi, T1, Pi, T1, and then the same goes for point x2. Okay, but we are restricting, so we are actually now restricting our integration along a certain surface, and this surface is simply given by, so we are right. So we are restricting ourselves on a surface which I define to be MF. And MF is simply an n-dimensional surface in the phase space M, given by the condition that Fi equal to a constant. So basically, I run from 1 to n. So if we begin with the 2n dimensional phase space M, putting n constraint in the 2n dimensional space, you ended up with an n-dimensional surface, which I call MF. Okay? So we are restricting our integral. So I think the picture should be something like, okay, so now we are considering some surface MF, then we are doing the integral between two different points on NF, and this is n-dimensional surface. Okay, so on this surface, that we can, because F are actually constants, we can actually solve. So yes. simply means those constant fi's. Yeah, sorry, I should specify notation. Yeah, okay.
Is S means the extreme?
No, here we're just generating functions.
Yeah, because I have a question. How do we know this is well defined? How do we see?
Well, yeah, I mean the Liouville condition will tell you this is actually well defined, which I'm going to specify momentarily.
Okay.
Good. So somebody asking whether this thing is actually well defined. Okay. So indeed, the punchline here is that whether this thing is actually well defined is to do with the fact, well, when you are doing the integral, well, for those of you who do complex analysis, you know that doing the integration on a high dimensional manifold, it depends on what path you are actually going, right? And whether a function is actually well defined as such, you only specify the endpoints. Then the function, whether it's well defined or not, it should be path independent. That whichever path you are actually doing should be actually independent of what you are taking. And precisely this Liouville theorem tells you that it's actually independent of which path we are actually taking when you go around the loop. Or if you want, you can recall from your vector calculus, this is basically a statement to do with the Stokes theorem, that when you calculate circulation around the loop, this thing vanishes, which is equivalent. And that's ensured by this condition. So, okay, so very good. So, so let's say, suppose this generating function for the canonical transformation actually exists. What's the consequence? Well, so if S exists, all right, so we can define that Pj is basically this guy, and psi j then we can write down an exact differential, just like what you would do. Actually, this guy you normally encounter in thermodynamics, if you recall. An exact differential do the following. And because this guy is the exact differential, d squared of that is 0, so that basically tells you that d for psi j, for psi d fj, is actually equal to swap the sign. Did I get, yes, I did get this wrong. Swap the sign. So that means the transformation is canonical. So that's provided f actually exists. Okay, so like somebody was asking whether this S actually exists or well defined, that's actually to do with the path independence when you're doing this integration as you defined. So the path independence basically path independent basically tells you that if you consider a closed path between, say, what I call Q, I guess I should call Q1 and Q2, like this. And the integral we are doing should vanish. And this is basically tells you, this can be ensured by Stokes theorem. So by